1, 0. All right. So in the 1800s, thereabouts, give or take, everything I read has a different year slightly. Someone said 1798, someone said 1802, I don't know. We had the billiard ball model, literally called the billiard ball model because it was one of the first conceptualizations of how the atom worked. It was around the time of Newtonian mechanics getting quite famous. And it was just this idea that particles were some sort of solid object that was very small, and they had tough, discrete boundaries, and they collided with things and stuff like that. And that sort of checked out for quite a few different things, except for the idea of electrical charges. And around heading into the 1900s, Maxwell's equations start becoming quite famous. Our understanding of electric charges and stuff like that become a bit more consolidated. And Thomson proposes the plum pudding model, which is essentially the idea that the positive and negative electrons and whatever should be attracted to each other. So they probably just all kind of hang out in a soup, all right? Now that actually makes a lot of sense when you think about it. Has anyone really thought about the model of the atom that we give you and gone, why the hell do protons stick together if they are all like charges? Right? We just tell you that. We tell you that in year 10. We tell you the protons are in the nucleus, the electrons orbit around the outside. Your response should have been, hang on. If the electrons are attracted to the protons, why don't they all just stick together? Great question. Eh? Right, angular momentum. The electrons have angular momentum. They're orbiting just like a planet. But is that sufficient? Wouldn't they eventually sort of fall in or fall away or be unstable or something? Well, they didn't really know. So they proposed the plum pudding model, which at the time seemed to sort of make sense. Positive and negative charges attracted, they make up the interior of the atom. Here was the big issue with this. They did an experiment, okay? Now the plum pudding model, this is actually a really bad diagram of it because it seems to indicate that the protons and the electrons are all kind of stuck together quite tightly packed. And that wasn't really the theory. The theory was that they floated around. They knew that atoms actually had a lot of empty space. They could actually pass atoms through each other pretty easily. They could shoot alpha particles and stuff through atoms and it passed through pretty easily. So they knew that atoms were actually mostly empty. There wasn't a lot in them. It was just a couple of protons and electrons or some positive and negative things within there, quite spread out and distributed. So they did an experiment. Rutherford, who's famous for the planetary model you can see there, did the gold foil experiment. Basically what he did was he took an alpha particle emitter, so something that emits alpha particles. If you remember alpha particles from nuclear physics back in year 11, they are helium atoms without electrons. They didn't know that at the time. All they knew was that it was a type of radioactive decay that was quite powerful. So really heavy. It's actually 2 protons, 2 neutrons. Again, they didn't necessarily know that at the time. Quite heavy, positively charged electromagnetic, nuclear radiation that was quite powerful. They likened it to a bullet as far as nuclear radiation was concerned. It was quite a heavy, big thing, okay? And they shot these quite large, powerful bullets at a tiny, tiny, tiny little sheet of gold foil, like aluminium foil, but made of gold. They knew that gold was fairly dense, had quite a large atom relatively, and so they were curious. They were like, well, if I shoot this alpha particle, which again is only positively charged, no electrons, not neutral, it's positive, right? If I shoot this, it should mostly pass through or sometimes deflect based off the plum pudding model, because the plum pudding model just says, you know, there might be a proton here or an electron there, but mostly it's empty space. And if this big heavy particle was pushing through, if it met another little individual proton, it'd probably just repel it within the atom. It'd shift out of the way. The alpha particle would go through, maybe slightly bounced, slightly deflected, okay? But what they found was most of the particles went through, no problem, as predicted, mostly empty space in the gold foil, no issues there. A ton of them bounced backwards. Now the analogy for this is if you shot a bullet at a piece of tissue paper and it bounced back and hit you. That doesn't make a lot of sense, right? So the plum pudding model sort of proposed that this gold foil was made up of these loosely packed protons and electrons in a mixed bag, and you should be able to move through it pretty easy. That wasn't the case. So the conclusion was the Rutherford model. They could actually calculate the angles of deflection, and this relates to Compton scattering. If you remember, we spoke about how electrons and light will scatter. Similar sort of idea here, except alpha particles, so particle-on-particle collisions, and they could accurately calculate the angular change in direction and predict that the center of the atom must be incredibly dense and be all positive. And then the rest of the atom was primarily empty space. Now, some follow-up experiment also investigated the idea of where the electrons could be and found, yeah, the electrons probably are sort of spread out around the outside. But what they did determine for sure was that the center was this positively charged, densely packed thing. And that's why our bullets were bouncing back. It wasn't a piece of tissue paper. It was like a metal ball with nothingness either side of it for a long time. And then a couple of electrons. So most of the alpha particles missed the dense nucleus, but the ones that hit it deflected substantially, which was not what Plum Pudding model predicted. Okay? So we came up with the Rutherford model. Pretty cool? Questions about that? No? Let's get this part down. I do not need you to draw that. It's just a little picture to help us appreciate it. Don't worry about that, but do grab the Rutherford model and the note about the gold foil experiment, which led to the Rutherford model down. Okay, so yeah, let's talk about exactly that. Why would they not fall to the center of the nucleus? There was two fundamental flaws with Rutherford's model. I do want you to copy this down. All right, copy that down. There's a second one. Okay, so that was the first one, right? Orbiting electrons should be highly unstable. They should spiral into the nucleus or fly away. If the idea of like the gravitational orbit was correct, it would be a very unstable thing for an electron which orbits quite quickly. Not like planets, which are huge, massive bodies, so forces affect them only very slightly. In this case, it would be much quicker. And it's actually worsened by the fact that Maxwell's wave equations at the time predicted that an electron that was accelerating, centripetal acceleration, but accelerating nonetheless, actually has to emit radiation as it accelerates because of a change in its velocity and therefore the electromagnetic field that it is oscillating in. So the wave equations at the time also predicted that it would radiate out energy as it orbited around through light. So it would be constantly emitting light, and it would lose kinetic energy. It would actually slow down. So even if it did get this perfect orbit, it would actually lose energy and slow down and end up spiraling into the nucleus as well. And that wasn't what we observed at all. It was very clear that electrons did seem to be separate from the nucleus of the atoms. And this didn't make any sense. That wasn't the only problem with Rutherford's model. Can anyone think of what else could be wrong with the Rutherford model? Say again? Neutrons. Neutrons were missing from Rutherford's model. Yes, that was a problem. That was resolved pretty easily, though. The neutrons didn't have a huge effect, but how did that come up? How did that come up? How did we know that orbitals must have been a thing? We have spoken about it, for the record. Why did Rutherford's model have to be wrong? And remember, this is back around the time that Maxwell's equations, which predicted electromagnetic properties of light, were not quite working out. Ultraviolet catastrophe, that sort of stuff. Say that again? Oh, the photoelectric effect? You're close, but you're backwards. You're backwards. Got it in reverse. So with Rutherford's model, the idea was, depending on its velocity, it could orbit at any distance, right? The orbital could be at any continuous distance. What did that not match with? They knew for a fact, wavelength, they knew for a fact that the radius of that electron's orbit was not continuous. How did they know that? How did they know that the Rutherford model had to be wrong? Because the Rutherford model predicted that the electron could orbit at any distance. It just had to change its velocity. Just like a planet. A planet could orbit really close to its sun, it just had to move faster. Or far away from the sun, it just had to move slower. How did they know that that wasn't what was happening with electrons? The discovery of quanta, right? The idea that light comes in discrete amounts. This was a fundamental problem for the Rutherford model. If the Rutherford model was the case, an electron could be so far away from the atom such that it had X amount of energy, and then it could change its position and emit a photon of whatever energy it wanted, depending on how its position changed in relation to the atom. That wasn't what happened. And in fact, certain atoms only emitted very specific wavelengths of light, very specific amounts of energy from different wavelengths of light. So the second problem was it did not explain how or why light was quantized. So how do we explain that now? In quantities, in discrete quantities, set amounts. Not 1, 1.1, 1.2, 1, 2, 3. I guess I should probably say it did not explain why the energy of light was quantized, but much of a muchness. Basically, it did not explain the concept of photons. It explained electromagnetic radiation, Maxwell's theories, but it didn't even do that very well because of problem 1. So it was this issue of, well, maybe Maxwell's right. No, but then that's a problem. Or, well, maybe Maxwell's wrong, but then this is a problem. Either way, it was an incomplete model. So how did they fix it? The Bohr model. Now, the Bohr model has been perfectly sufficient for us for a very, very long time. And it's only recently that the quantum model has come along. But the Bohr model does actually explain a lot of quantum mechanical properties. And we're actually going to sufficiently use the Bohr model for a lot of what we will do. Okay, and this is the problem. When you heat up a hydrogen atom or collection of atoms, you can give it enough energy such that it begins to emit light, begins to radiate light. Some of that light can be visible. Of course, you guys know that actually a lot of it's probably not visible, but whatever. If you look at the wavelengths of light emitted by an atom, you only get fixed or discrete wavelengths of light. Kind of crazy. This is the whole idea behind quantum light. Light, when emitted from an atom, only comes in fixed amounts. And this is for every atom. Doesn't matter what element it is. There is not an element on this earth that you can heat up such that it will produce a certain frequency or wavelength of light. They only ever produce set wavelengths and frequencies. They can produce quite a few. Some of the larger, more complex atoms can produce some pretty crazy combinations of wavelengths of light. But hydrogen, for example, barely produces any at all, and some are exceedingly rare. So. If you heat something up, it emits light. How hot it is will change the type of light it emits, but it can only emit light of set frequencies depending on what the material is. And look this way in 0. Does that conception of the Bohr model adequately explain that? Can you see how the Bohr model resolves that issue? So what was our first problem with Rutherford's model? Right, so the Bohr model just proposes that they exist in energy levels. So they can't fall in. Yep, good question. Good question. Yeah. Well, so this didn't have levels to it. It just sort of said that they could orbit like planets, the planetoid model or the planetary model. So they could orbit at any distance just depending on their angular velocities. So the first problem with Rutherford's model is not actually really resolved by the Bohr model. They just kind of said the electrons exist in what's called stationary states, and we're going to make some notes on this in a second, but they exist in stationary states. So they are fixed in these levels. They can only be here or they can only be there. So that solved the problem, even though it didn't really make sense, but it solved the problem as a concept, as a model. What was the second problem with Rutherford's model? Right, it didn't explain this. How does Bohr's model do that? Does anyone know? Set energy levels, which means set energies of what? The electron first, but then how is the set energies, and remember, the energy of an electron is not the same as the energy of a photon. Photons have their frequency, that's their energy, they're massless particles, they have momentum, but it doesn't come from a mass or their velocity or anything, they travel at the exact same velocity at all times. Electrons, on the other hand, are physical particles that have mass and they have velocity, so they have angular momentum. So they have some sort of kinetic energy here, okay? That kinetic energy is now being quantized. They can only exist because they all have the same mass. So if they're x distance away from the atom, if their radius is whatever, they have to have enough velocity to maintain that orbit. This is the argument, right? If you then make them a fixed distance further, so let's say it's 1 by 10 to the negative 30 meters away from the atom, right? And then it becomes 2 by 10 to the negative 30 meters, the amount of kinetic energy they have jumps up in a discrete amount, okay? How does that then relate to light emitted? How does a Bohr atom emit light? We heat it up. What does heating it up do? Gives what more kinetic energy? The atom, which is understood through the kinetic energy of the... Now in the Bohr model, if we give an electron more kinetic energy, what's it going to do? Go into a higher energy level, right? Enter another energy state. You have to give it the right amount of energy, which is what the photoelectric effect proved. We need the right amount of energy, and then we can bounce it up to a higher energy state. In the photoelectric effect, the energy state we were looking for was complete ionization, emission of the electron. But if we don't fully ionize the electron, we can bounce it into a higher state, and it can just sit there for a second with more energy. What's going to happen, though? Are you saying it, Michaela? I feel like you just said what I'm looking for. Oh. Do you know why, once we get that electron into a higher energy state, what it will do and what that has to do with discrete packets of light? No? Anyone? I feel like it's come up before. What's going to happen if it jumps up? Let's say we take this electron, right? And we give it energy, it goes into a third shell. What's it going to do? You're thinking photons. Careful thinking of photons. You're actually not wrong, but wait, we don't need to think about it. If it's in a higher energy state, is it just going to stay there? Is that energy just going to stay as kinetic energy in the electron? Why not? Right. So it's going to go back down. So atoms always exist in a ground state. If they are ionized such that their electrons go into higher energy states, they will actually then release that energy as the emission of a photon. So Maxwell was kind of right. These electrons will collapse towards the center, just not all the way, just only to the smallest energy level. And he was also right that when they do collapse to the center, they do emit energy as electromagnetic radiation. But it can't be a continuous wave amount. It has to be a specific amount that is exactly the same as the kinetic energy that the electron must lose when it goes into a lower energy state. Okay? Let's look at a quick example. This is a ground state. Does anyone know what atom this is? What element? Is my electromagnetic wave. I know, it's beautiful. Now, quick point. When we generally talk about this type of increase in electrons' energy level, the radiation that we use to do this is generally pretty small energies, okay? Which is why we often talk about heating things up to do this, because heat is infrared electromagnetic radiation, quite a low frequency of radiation. Infrared is one of the lower energies of electromagnetic radiation. In the photoelectric effect, where we're actually hitting these electrons so hard that they blasted and fell off, we're often talking about ultraviolet light, much higher energy light. Because if we actually just give things low energy light, we don't emit the electrons and create the photoelectric effect, but we can raise their energy states and they will then decay and re-release energy. Now, very simple example of this is if we do this. Oh, that's too big and the wrong color. Maybe it wasn't too big. Okay, so have a look at that. We've hit this atom of lithium. The ground state of lithium looks like that. We've hit it with electromagnetic radiation, and we've increased the energy of the electron. So it's gone into the third shell, okay? So it's actually jumped up into a higher energy level. For it to be further away from the atom, it has to have higher kinetic energy. So it's absorbed that electromagnetic radiation as energy, and it's used that energy to exist in a higher energy state. But it will then decay. All right, so this is the idea, right? If we take a ground state of lithium, we blast it with electromagnetic radiation. Again, generally in this case, we're not trying to totally ionize this electron away from its atom. So we would use heat, which is lower wavelength, higher wavelength, lower frequency, lower energy EM radiation. When we heat this up, we can raise that electron into a higher energy state. It's no longer in the ground state. It's in the third energy shell, okay? You could do it subsequently with inner electrons as well. It's quite possible, but let's just focus on that for now. Then, in that state, it does become unstable, and it will decay. And when it decays back to its ground state, it drops back to that energy level, it loses a very specific amount of kinetic energy dictated by the energy levels it can be in. It's dropping from the third shell to the second shell, so it's dropped, let's say 1 by 10 to the negative 30 meters, right? It's dropped a set amount of distance, and that changes its kinetic energy by a set amount. Now, when that kinetic energy is lost by the electron, it has to be lost somehow. Conservation of energy has never been disproven. So it emits radiation, electromagnetic radiation, in the form of, well, that depends on the atom and how much energy it releases it in. It could just re-radiate heat, as is the case for our Earth, which we sort of conceptualize as a black body. It emits infrared radiation. You guys emit infrared radiation because your atoms are constantly being heated up by other things, by the lights around you, by the sunlight, and occasionally they then re-emit radiation. Big difference between emission and reflecting, right? The reason I can see you guys in visible light is not because you are emitting high energy light in the visible spectrum, right? You are only actually emitting probably infrared light of very low energy, but you're reflecting a ton of other light. Okay, so do we see how Bohr's model sort of solves some of those issues with the Rutherford? Now, there's still that big problem of, well, why do the electrons not fall into the nucleus? I'm not going to answer that yet.
That's the one thing I actually want to do.
I will tell you.
Wait, what is
I will tell you when we do. So this is just giving energy to an atom, that energy being absorbed by the atom and transferred to the electron by increasing the energy level it exists in. And this is what the Bohr model was based upon, these discrete energy levels. I'm really bad at pausing. All right, thanks, guys. If you're still getting your notes down, keep doing so. You're just going to have to do two things at once. So here was one of the major sort of proposals of the Bohr model. Angular momentum how do you spell it? Was equal to, I think they used Al most of the time, which was equal to mass times velocity times radius, which was equal to a number times by Planck's constant divided by 2 pi. That's it. Now, I believe that is given in your formula and data book. Where m is electron's mass, v is velocity, obviously. Do I need to write that? You guys are fine with that, right? R is radius. Could be worth doing that just in case. We're about to use a capital R for something entirely different, so. H, Planck's constant, don't forget. I'm sure you know what pi is, but what is n? What does that mean? A number. Better be good. Collisions. We're talking about the Bohr model. And we're talking about the angular momentum of the energy state that it's in, okay? And that is a discrete number. It can be an energy level 1, energy level 2, energy level 3, okay? A discrete number, we now have quantized momentum of electrons. So for those of you who are a bit chemistry minded, your shells. If you're in the first shell, n equals 1. Second shell, n equals 2. Here's a nucleus. Don't want an oval. We don't do hilariously, if you're thinking of your p and your s orbitals and stuff. They're called quantum orbitals. We actually don't do quantum orbitals in quantum mechanics for matter. It's just Bohr model energy levels. Hilarious, I know.
Did you say hilariously?
I said it's hilarious.
You said it's hilarious.
I said hilariously, we don't do that. Hilariously. No, that's a genuine word. You can say hilariously, we don't do that.
How's it spelled?
Hilarious,
Is it like H-I-G?
L-Y.
What?
Hilarious, L-Y. Hilariously, having the property of being hilarious. It's a thing.
No, it's not. Hilarious.
It's a thing. Fact check me. All right. What'd you just say? Coming for you, kid. You haven't got your results yet.
I didn't do it.
No, guys, you did really well. I'm pretty happy. I will warn you, these results are tentative. And I've given you the grades I think you should get, but they haven't been confirmed, so take them with a grain of salt. You can get them from me in 5 minutes. Let's just finish our notes. Campbell, you probably do. Who was that?
I didn't do a bibliography.
I had to monitor Tom's. I was very close to pulling him down. Hilariously, I think Mr. Macaulay monitored yours, actually. I genuinely can't remember what you got. What the hell? Oh, I thought it had made a diagram for me of little protons. How did I put a cross there? Oh, that was element X. Oh, okay. I must have done something stupid. What did I do? There. That's what it should have been. So n equals energy levels. That formula, therefore, can tell us the angular momentum, and I'm sure you can imagine that we will very likely relate that to electrons' energies, and therefore quantum states of photons being emitted. Now, we're going to do, it'll be a couple of formulas, and one of the formulas looks really ugly, but when we look at a Bohr diagram to understand it, it makes sense, but you don't have to draw the Bohr diagrams. All right, let's do one quick example. Am I still recording? I keep forgetting. I've been recording this entire time. All right, cool. About monitoring people's assignments. Oops. I really have to get good at editing things out, but it just takes so much effort.
That's my point.
Okay.
No, don't, because then she just cut out all the parts where she gets yelled.
All right. Worked example. Is that the one? There's one video on our channel that has significantly more views.
It's me and Kobe just looking at people getting roasted.
It's a bit sad, gentlemen.
So funny. It was hilarious. She got so mad at me.
You make me feel guilty for putting it up. All right. Calculate the angular momentum. Find L for N for hydrogen when the electron is in the second orbital. Let's do first and second if we get time. We should. Okay, what formula do I want? NH on 2 pi. That's the only part I'm interested in. I'm not going to use the MVR. I don't know the radius and stuff like that. This is actually the way we can find the velocity and find the radius because we know the mass. But we need to find L. Which color do I want? Blue. We want L, so we're going to use L equals NH on 2 pi. Look how easy this is. 1 times 6.626 by 10 to the negative 34 on, oops, 6.28 or 2 pi. I'll just leave it as 2 pi. Chuck that in a calculator. What do you get? (1.05) times 10 to the negative, does it stay 34? Yep. That's the angular momentum. Kilogram meters per second, momentum. Oh, it is angular momentum, which is meters squared per second, because it's constantly accelerating meters squared. Now, here's the cool thing about this. Your answer, just double it. It's discrete quantized things. So the second energy level is just twice as much as the first energy level. That's the crazy part of this. So this is for L when n equals 1. L when n equals 2, just equal to 2 times that. 2.1. What'd you get? 3.57. Did you get 1.05 for n equals 1? Yeah. Sorry, Hannah? You triple it. Triple n equals 1. Yeah. Or you could 1.5 times n equals 2 if you felt like being weird and wacky. Woo! 2.1. Kilogram meters squared per second. It's there. I swear, that's the units there. I squeezed them into the corner there. Like a Banksy? What's his name? Like his signature. Corner there. Don't mind me. All right, any questions about that? Pretty straightforward little formula there. Again, you can use that to find, the velocity of the electron in that orbital. You can use it to find the radius at which the orbital is. All sorts of cool things.